National Grid ESO has just released their latest Future Energy Scenarios report. This is a 170-page document and accompanying workbook covering different generation and demand pathways out until 2050 for the GB energy market. This year, the biggest takeaway was flex. Now, we know that flex is critical as we transition to a net zero grid. It's flexible assets from battery storage, electric vehicles, and demand-side response that ensure we can keep the lights on when the sun isn't shining and the wind isn't blowing. However, what is especially interesting in this year's report is how much NESO's flex predictions have increased compared to 2024, and how much of this is consumer-led flex. In NESO's holistic transition scenario, they're now predicting up to 40 gigawatts of utility-scale battery storage by 2050, up 4 gigawatts from their 2024 projections, while their forecast for V2G flex has increased by 28% to 41 gigs. Taking into account all sources of flex, including interconnectors, almost 50% of the total system flexibility will come from residential and commercial consumers. While flex is vital, not all flex is equal. If assets are controlled by overly simplistic energy management systems or not exposed to dynamic tariffs or markets, then those assets aren't creating as much value as they could be. To illustrate this, we ran a model in Gridcog comparing a small supermarket in London operating their flexible assets in different control modes. Our supermarket has a number of energy assets on site, including battery storage, solar PV, flexible refrigeration, and a small electric delivery truck fleet. In our baseline scenario, these are all operating in simplistic control modes, with our battery in self-consumption mode and our EV fleet charging at full power as soon as it gets back to the depot. This site is on a standard retail supply contract with a peak and off-peak rate. In our second scenario, we've altered the control mode of our battery to be in co-optimize mode and our EV fleet to start smart charging. Here, they'll respond to price signals from the retail and network charges that the site is exposed to. The time of use element from the retail supply and network contract should reflect system scarcity, with peak pricing over the likes of winter evening peaks. When taking a look at the results of this model, we can see radically different asset behaviour. To service the loads on site in our baseline scenario, the site has a maximum demand of almost 400 kilowatts, whereas in our second scenario, this falls dramatically to 67.5 kilowatts. This is a response to the assets responding to off-peak price signals and peak demand network charges. This saves 300 kilowatts of grid connection capacity, which is massive in terms of cost, resource efficiency, and speed. Not only are our assets using less grid connection, but we can see that the site's demand is heavily concentrated overnight, a period of typically lower demand. This again shows price signals and flex assets working to keep the whole energy system in balance. Finally, we know flex assets can participate in many other energy, ancillary, reserve, balancing, and capacity markets. But we kept things deliberately simple here. Even so, looking at our cash flow results, only altering the control mode of our battery and EV fleet saved our supermarket owner 10% of their energy costs in just 1 year. NESO's latest Future Energy Scenarios report underscores how crucial flex is to achieve net zero. However, as we've seen today, flex assets are only as good as their control mode and the price or market signals that we provide them. If you want to learn more about modelling markets and smart tariffs for smart assets, then get in touch.